The learning objectives for Chapter 12 Vectors 2 would be to find vector and Cartesian equations of lines and to look into the applications of equations of lines. Now, before we actually define what lines are in vectors, let's take a look at this particular diagram. There are 2 points A and B. The 2 points A and B can be represented by two non-zero, non-parallel vectors with respect to the origin O, namely by the vector A and the vector B. The two vectors can be added together by using the triangle law of vector addition to obtain another vector, what we call the vector R. So in this particular diagram, if we were to take a portion of vector B, for example, lambda B, right? The vector lambda B is parallel to B. By applying the triangle law of vector addition, the vector A plus lambda vector B, we will be able to get the vector R, which represent the point R as noted. By changing the values of lambda in the next few examples, we're going to see that the position vectors of the points representing the point R will actually change. So we're going to look at that in the next moment. Let's take a look at part A. As noted before, the position vector of the point R is represented by this relationship. So for the different values of lambda 0, 1 and 2, we would actually have different representation of the position vectors of the point R. When lambda equals to 0, R equals to A. Lambda equals to 1, R equals to A plus B. Lambda equals to 2, R equals to A plus 2B. Now, based on the diagram, by applying the triangle law of vector addition, when we take the vector A, add to the vector B, we will actually obtain the vector R as shown here. And that actually represents the point R situated over here when lambda is equals to 1. When lambda equals to 2, we notice that the vector A is added to 2 times of vector B, and this itself, by using the triangle law of vector addition, will actually represent the vector R, which represent the point R situated over here when lambda is equals to 2. So let's take a look at part B. In part B, the values of lambda given are -1, 0 and square root of 2. So with those values of lambda, we actually have the position vector of the point R given as R equals to A plus negative of B, R equals to A, R equals to A plus square root 2 of B. Let's take a look at the position vector of R when lambda is equals to -1. Now, when lambda equals to -1, the position vector of R is given as the vector A added to the vector -B. So in this particular diagram, the vector -B has the same length with the vector B but opposite in direction. So by applying the triangle law of vector addition, A plus -B, we will actually get the position vector of the vector R as noted here, representing the point R situated over here when lambda equals to -1. When lambda is equals to square root of 2, we are actually adding the vector A with the vector square root 2b. Square root 2b has the same direction as the vector b but different in length. So when we add the vector a to the vector square root 2b, the resultant vector is given by this vector over here, which represents the point situated over here when lambda equals to square root 2. So once again, we can see that by changing the values of lambda, we actually change the position of the point r from here to here and to here. And we now are able to notice that the point r actually lies on this particular line that you see here. In part C, we are given the values of lambda belong to the set of all real numbers between -1 and 1, inclusive of -1 as well as 1. Now, when lambda is equals to -1, the position vector of this point is described by this vector. When lambda is equals to 1, the position vector of this point is described by this vector. So from here we realize that when lambda changes from -1 to 1, a line segment is formed between this point to this point. In part D, when the value of lambda belong to the set of all real numbers, we realize that an infinite line is formed instead of just the line segment as in part C as observed over here. Therefore, for any points on the line, the position vector of each point on the line can be described by this expression by varying the values of lambda. So for instance, when lambda is equal to lambda 1, this particular point has position vector a plus lambda 1b. When the value of lambda is equal to lambda 2, as in this instance, this particular position has a position vector a plus lambda 2b. And lastly, when the value of lambda is equal to lambda 3, this particular point has position vector a plus lambda 3b. So when we change the values of lambda for all real numbers, we will describe all the different points on this particular line. So how do we describe the vector equation of a line? Now in this section, we are given a point on the line and a direction vector parallel to the line. So consider this particular line L. This line L passes through the point A with position vector with respect from the origin as A, and this line happens to be parallel to the vector D. Now this vector D is what we call the direction vector of the line L. Now if we let R represent any point on line L, the position vector of the point R is represented by this vector R. Now from this diagram, since D is parallel to AR, therefore we can write the vector AR equals to a scalar multiple of the vector D for some values of lambda in the set of all real numbers. Thus, the vector OR, by using the triangle law of vector addition, the vector R equals to the vector A plus the vector AR, as what you see here. Since we have already written that the vector AR equals to a scalar multiple of the vector D, thus the position vector of the points R which lies on this line can be written as this form. So in short, the vector equation of a line is typically expressed in this form: R equals to A plus lambda D, where lambda is a set of all real numbers. R actually represents the position vector of any points on the line L. A refers to the position vector of a known point on the line L, and D refers to the direction vector of the line L. So in short, in order for us to write down the vector equation of a line, we need a point on the line that is the position vector of one particular point on that line, and we also need the direction vector of the line. So with these two components, we can actually form the vector equation of the line. Now in the next instance, we are given two fixed points on the line. So for example, in this particular diagram, the line L passes through the point A with position vector A, and also passes through the point B with position vector B. The vector equation of the line L can be written as A plus lambda B minus A, or B plus mu B minus A. As before, in order for us to form the vector equation of a line, we need one point on the line, and we also need the direction vector of the line. So in this particular case, one particular point that we know to be on the line is actually the point A itself, so we can use the position vector of the point A. The direction vector of the line in this case is just the vector AB. Another way of writing the vector equation of this same line is actually using another point on the line. So for this particular case, another point that is actually on the line itself is actually the point B, so we can use the position vector of the point B. And of course, to complete the vector equation of this line, we need the direction vector of the line itself. Do note that vector equation of a straight line is not unique. As what you can see here, this same line can be represented in this form and also in this form. In fact, there are many more variations for the vector equation of this same line. For example, if you don't wish to use the direction AB, you could also use the direction BA instead of the direction AB. So therefore, you can replace B minus A with A minus B. As long as the direction is parallel to the direction of the line itself, we can use it as the direction vector of that particular line. Now if the line passes through the origin and the point A, the vector equation of that line will actually be represented by this expression. R equals to the origin having the position vector as 0 plus lambda, and we need the direction. In this case, because the origin actually lies on the line, therefore one direction is just the direction OA, and this can be simplified to lambda OA. A quick example is this particular example over here. Things through. In example 1, we are supposed to find a vector equation of the straight line passing through the points A and B. The points A and B have position vectors given as 5, 2, 6 and negative 3, 6, 2 respectively. So in order for us to form the vector equation of the line, we need to find the direction vector of the line, and we also need to identify one particular point on the line. So for this particular question, since both A and B lies on the line, we could actually use either A or B to be the point on the line. Alright, so to form the equation of the line, first we need a point on the line. So in this case, we can choose 5 to 6. We can choose a point A. And to complete the vector equation of this particular line, we need the direction. So for the direction, we're going to use the direction vector parallel to the vector AB itself. So to form the vector equation of the line that passes through the point A and B, we need one particular point on the line. So in this case, we have chosen the point A. So therefore, we use the position vector of the point A. And we need a direction parallel to AB. We found that the vector AB is given as negative 8, 4, negative 4. So instead of using negative 8, 4, negative 4, we actually use 2, negative 1 and 1. Right, because that is enough to be the direction vector of this line, because 2, negative 1 and 1 is actually parallel to negative 8, 4 and negative 4. So we can use 2, negative 1, 1 as the direction since it is parallel to this particular line. That being said, this is not the only way that we can write the vector equation of this particular line. So all these variations are also acceptable. Alright, to check whether a point lies on a given line, what we need to do is we check whether the point satisfies the equation of the line. To check whether a point satisfies the equation of the line, what we need to do is to check whether there is consistent value of the parameter lambda for all the three components x, y and z. I will let you read example 2 on your own to see how we can check whether a point lies on a given line. Alright, in example 3, we are asked to verify whether this particular line passes through the point with coordinates negative 7, 8, 0. So drawing a simple diagram, we have this particular line. One point on the line has these coordinates 5, 2, 6, which we actually get from here. The direction of the line, which is 2, negative 1, which we get from here. So we want to check whether this particular point, as noted down here, actually lies on this line. So as previously mentioned, in order for us to check whether this point is on that particular line, what we need to do is to see whether this particular point satisfies this equation. So the equation of the line can be written in this form. Alright, so in order for us to check whether this particular point satisfies this equation, what we need to do is to consider whether the point actually satisfies the equation, and we write it in this way. Alright, written it in this way, we need to check whether the values of lambda for the x component, for the y component and for the z component are all consistent. So what we need to do is to form three equations. For each of the component, we need to evaluate what is the value for lambda. So for the x component, we can see that the value of lambda is equals to negative 6. For the y component, the value of lambda is equals to negative 6. So far so good. And lastly, for the z component, the value of lambda, it is still negative 6. Since the value of lambda is consistent for all the three components x, y and z, we therefore conclude that the point with coordinates negative 7, 8, 0 lies on the particular line over here. Alright, in example 4, we are supposed to find a vector equation of a line L. The line L actually passes through the point A. The point A has this position vector 4, 0, 1. And the line L is parallel to the vector 1, negative 1, 2. for this particular question, we label the direction vector of this line as the vector D. So we're supposed to find the vector equation of this line L, and then for the second thing that we need to do is to find the coordinates of the 2 points on the line L itself, such that the distance of those points is actually square root 35 units from the origin. Alright, so first and foremost, we need to find the vector equation of the line L. So as we have covered before, we need one particular point on the line. So in this case, the obvious point to use is the point A. So we use the position vector of that point A, so 4, 0, 1. And then we need a direction parallel to the line. So as stated, this is the direction vector of the line, so we're going to use it. Alright, so this is the vector equation of the line L. So using a simple diagram, the point A lies on the line L. The direction vector is given by D. So any points on the line, we label it as R, would have the coordinates given as this, which is actually taken from the vector equation of the line itself. So for any arbitrary point R on the line with the coordinates written as this, the position vector of the point R based on the vector equation of the line is actually written in this form. So OR has this position vector, and therefore the magnitude of this vector is actually given by this formula that we have seen before in vectors 1. So according to the question, this OR, the distance from O to the point R, has magnitude equals to square root of 35. So in order for us to find what is the value of lambda, we need to solve for this particular equation. So solving this particular equation, we are able to get the values of lambda equals to 1 and lambda equals to negative 3. So there are 2 points on the line, which is actually square root 35 units away from the origin. Alright, so for the first point, when lambda is equals to 1, the position vector of that point is given by 5, negative 1, 3. So therefore, the required coordinates of this particular point, which is square root 35 units away from the origin, is actually 5, negative 1, 3. So when lambda is equals to negative 3, the position vector of the point R is given as this 1, 3, negative 5, and therefore the coordinates of the next point, which is square root 35 units away from the origin, has these coordinates 1, 3, negative 5. In this section, we're going to look at the equation of lines in other forms other than the vector equation form that we have covered. The two other forms of the equation of lines will be parametric equations and Cartesian equations. Now, for vector equation of the line L, if the line L passes through a point A with coordinates A1, A2, A3, and the line L is parallel to the direction vector D1, D2, D3, if we let the point R with coordinates x, y, z be any point on the line L, then the position vector of the point R can actually be written as the column vector x, y, z. And this can be broken into the individual components along x, y, and z as what we see down here. So in this case, from the first line, we get x is equals to a1 plus lambda d1, y equals to a2 plus lambda d2, z equals to a3 plus lambda d3. The format that you see here for the equation of line is called the parametric equation. The reason that this is called the parametric equation is because each one of the components in this equation contains the parameter lambda. We will now look into the third form of the equation of line called the Cartesian equation. From the parametric form of the equations, by making lambda the subject for each one of the component, we actually have these expressions being equal to each other. Writing that as a single equation, we have x minus a1 divided by d1 equals to y minus a2 divided by d2 equals to z minus a3 divided by d3. Now this is called the Cartesian equation of line. If you notice in this form of the equation, the only variable that you see are x, y and z. You don't see the parameter anymore. So in this case, this is what we call the Cartesian equation of line. We have now covered the three types of equation of lines. The first one, the vector equation, is of this form. The second one, the parametric equations, which contains lambda for each one of the equations. And the third one, the Cartesian equations, which contains only the variables x, y and z, and it does not contain the parameter lambda. To convert the vector equation to the parametric equation, what we can do is, for each one of the component x, y and z, we form the equations as such. To convert from the vector equation to the Cartesian equations without going through the changing to the parametric equations, what we can do is to observe the pattern that we can see over here. By looking at the vector equation, a1, a2, a3 can be found in the Cartesian equation a1, a2, a3. For the component referred to in the vector equation for the direction vector of the line, d1, d2, d3 can be found on the Cartesian equation in d1, d2, d3. So by observing this pattern, we can convert the vector equation to the Cartesian equation vice versa directly. Now in example 6, we are asked to find the Cartesian equations of the line L. In part 1, the equation of the line L is given as this, and in part 2, the equation of line L is given as this. So let's take a look at the Cartesian equation of the part 1 first. Now the Cartesian equation of the line L has this format. Alright, so if you remember the pattern as previously discussed, we can look at the component 3, negative 1, 0 are to be placed over here. And the direction vector component 2, 4 and 1 are to be placed over here. So therefore, the Cartesian equation of the line can be directly written as x minus 3, y minus negative 1, z minus 0, divide by 2 over here, divide by 4 over here, and divide by 1. We can further simplify this to x minus 3 divided by 2, y plus 1 divided by 4, and just z over this side. Now for part 2, alright, we can do the same thing. Okay, so for the component over this side, negative 1, 4 and 3, for x we can actually place it over here, and then for z we can place it over here. For the direction vector component, negative 2, 0 and 1, similarly for the x component we can place over here, and for the z component over here. For part 2, we notice that y is always equals to 4. So therefore, we will need to put down y equals to 4 first. And then we can start to put in the other components. So we have x minus negative 1, z minus 3, and minus 2 over here, and 1 over here. We can therefore further simplify this to y equals to 4, x plus 1 divided by negative 2 equals to z minus 3. Now let's convert the vector equation to the Cartesian equation directly. So for the component 1, 2 and negative 3 is going to place over here, and for the component 4, negative 5, 2 is going to place over here. So we would have 1, 2 and negative 3, 4, negative 5 and 2, and this can be simplified to x minus 1 over 4, 2 minus y over 5, z plus 3 over 2. For the next question, question 2, for the component 2 and negative 3, we're going to put at here. For the component negative 5 and 2, we're going to put it here. So we will have y minus 2, z minus negative 3, here is negative 5 and here is 2. So what happens to the component for x? So if we were to look at the components for x is always equals to the value of 1. So for this case, x is just equals to 1. For the third equation, we realize that x is always equals to 1, y is always equals to 2, and z is always equals to lambda. Because we are only looking at the Cartesian equation, and we know that the Cartesian equation shouldn't have any parameter in the equations, so we will actually not include z equals to lambda as part of the Cartesian equation. So the Cartesian equation for question number 3 is just x equals to 1 and y equals to 2. In this section, we are going to look at the relationships between two lines. Let's say we have two lines L1 and L2. The equation of L1 is given as so. The equation of L2 is given as so. There are three possible relationships between these two lines. The first one, the two lines are parallel lines, that is, they are coplanar, lying on the same plane. Now parallel lines L1 and L2 are parallel if and only if the direction vectors for the two lines are parallel to each other. That is, the direction vector of each one of them can be written as a scalar multiple of the other for some values of k. The two lines are intersecting lines if they share a common point between them. For example, if L1 and L2 intersect at some point P, the point P can be found on both L1 and L2. If that is the case, the position vector of the point P can be represented by the equation of L1 as well as the equation of L2 for some real values of lambda and mu. The third relationship between lines would be the skew lines. Now what are skew lines? First, the lines are non-parallel, and second, the lines are not intersecting. So how do we visualize skew lines? So in this particular diagram, we can observe that the line segment GE and the line segment AC are both not parallel and also not intersecting. They are therefore skew lines. If we look at these two lines, AC and this blue line here, these two lines are actually intersecting because, as we can observe, these two lines are on the same plane. However, if we were to bring down this line down towards GE, we notice that GE itself is on a different plane as compared to the line AC, which is on another plane. So GE and AC are GE and AC are non-parallel and also non-intersecting, and therefore they are skew lines. Now we can use this simple flowchart to determine whether two lines are either parallel, not parallel, intersecting, or skew. So given two lines L1 and L2 with two equations like this, the two lines are parallel if, let's say, the direction vectors can be written as a scalar multiple of the other. However, if the direction vectors cannot be written as a scalar multiple of the other, then L1 and L2 are not parallel. If L1 and L2 are not parallel, then L1 and L2 could either be intersecting or skew. Now, to determine whether the L1 and L2 are intersecting or skew, what we need to do is equate the two equations of the two lines and check for the values of lambda and mu. If the values of lambda and mu are consistent, then L1 and L2 are intersecting. However, when lambda and mu values are not consistent, then we can conclude that L1 and L2 are skew. Alright, in example 8, we are to determine whether the following pairs of lines are either parallel, intersecting, or skew. And if the lines intersect, alright, we are supposed to find the position vector of that point of intersection. So let's take a look at part 1. In part 1, the two equations for L1 are given as this, with direction vector 1, negative 2, 3. And for line 2, the direction vector is negative 2, 4, negative 6. So if we were to look closely at the direction vector for L2, negative 2, 4, negative 6 actually can be written as negative 2 times 1, negative 2, and 3. If that is the case, so that means the direction vector can be written as a scalar multiple of each other, which means that the two direction vectors are actually parallel, and hence L1 and L2 are parallel. For L3 and L4, if we were to look at the two direction vectors, 1, negative 2, and 3, negative 3, 2, and 1, we realize that they cannot be written as a scalar multiple of each other. So since this direction vector cannot be written as a scalar multiple of the other direction vector for all real values of k, we can decide that the two direction vectors are not parallel. Hence, we can say that the two lines are not parallel. So if they are not parallel, then we need to check whether they are intersecting or skew. So to check whether the two lines are intersecting or skew, what we can do is to equate the two equations as so. By equating the two vector equations, we can actually form a set of simultaneous equations as so. So for the x component, we can write it as lambda equals to negative 1 minus 3 mu. For the y component, we can write it as 1 minus 2 lambda equals to 11 plus 2 mu. And for the last component, the z component, we can write it as 3 lambda equals to negative 23 plus mu. So simplifying the equations as so and solving for equation 1 and equation 2, we are able to get the values of mu equals to 2 and lambda equals to negative 7. So to check for consistency in the values of mu and lambda, we are going to take these two values and substitute into the third equation and check for consistency. From equation 3, we realize that the left hand side is actually equals to the right hand side after substituting the two values. So therefore, we can conclude that the values of lambda and mu are consistent, and hence the two lines L3 and L4 therefore are intersecting, and therefore we can actually find the position vector of the point of intersection by substituting either mu equals to 2 into here or lambda equals to negative 7 into here. Alright, so what we can do is we can choose lambda if we wish to, alright, and put it into the equation over here to get the position vector of the point of intersection. For part 3, the two lines L5 and L6 has direction vector 2, 1, 1, negative 5, negative 1, 3. So similarly to the previous part, we realize that the two direction vectors cannot be written as a scalar multiple of each other. Right? So from there, the two direction vectors are therefore not parallel, and hence we can say that the two lines are not parallel. Now, since they are not parallel, we want to now check whether the two lines are skew or intersecting. And the method to do that, as in the previous example, is to equate the two equations together. By equating the two equations together, we can form the set of simultaneous equations as shown here. Simplifying the set of simultaneous equation into this form and solving for equation 1 and 2, we found the values of t equals to 1 and the value of s equals to negative 2. Now we want to check whether these two values satisfy the third equation. So from the equation 3, we actually get the left hand side with the value of s equals to negative 2 and t equals to 1. We obtain a value of negative 5, which is not the same as the value on the right hand side. So we can say that the values of lambda and mu are inconsistent, and therefore conclude that the lines L5 and L6 do not intersect, and therefore they are skew. So for a skew line, we must make sure that the two lines are, number one, they are not parallel, and then we discover that if they are not intersecting, then we can conclude that the two lines are skew.